Imagine this. You're looking at the night sky, a canvas of stars and galaxies stretching out as far as you can see. But here's the mind-blowing part. What you're seeing is just the tiniest fraction of the universe. In fact, it's like looking at a single grain of sand from a beach that goes on forever. Beyond what we can observe lies a vast, mysterious expanse that we are only beginning to understand. So, what's out there? What secrets does the edge of the observable universe hold? Stick around, because we're about to take a journey to the very limits of human knowledge and beyond. Definition of observable universe, tied to light travel limits. The observable universe is a vast, mind-boggling concept that refers to the region of space that we can currently see and study. It's not the entire universe, just the part we can observe. The size of this observable universe is tied to the speed at which light travels and the age of the universe itself. Light takes time to travel through space, and the further away an object is, the longer it takes for its light to reach us. This means that when we look at distant objects, we are actually seeing them as they were in the past. For instance, the light from the sun takes about 8 minutes to reach us, so we see it as it was 8 minutes ago. Similarly, the light from the nearest major galaxy, Andromeda, takes about 2.5 million years to reach us. This delay is crucial because it sets a limit on how far back in time we can see. This light travel limit is why the observable universe is finite, even if the entire universe is not. The universe is estimated to be about 13.8 billion years old. In that time, light could have traveled a maximum distance of about 13.8 billion light-years. However, due to the expansion of the universe, the current distance to the edge of the observable universe is now about 46 billion light-years. This might seem counterintuitive, but it's a result of the universe expanding while the light was traveling towards us. Think of it like this. If you're in a car and you throw a ball straight up, by the time it comes back down, the car has moved forward, and the ball lands behind you. Similarly, the universe has expanded while the light was on its journey, making the edge of the observable universe much further away than the initial 13.8 billion light-years. The observable universe is also not perfectly spherical or evenly distributed. It's shaped by the distribution of matter and energy, as well as the curvature of space-time. Our understanding of the observable universe is also limited by the technology we have. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope have allowed us to see further and more clearly than ever before. They've helped us observe galaxies that are so far away that their light has been traveling for over 13 billion years. Yet, there's still so much we don't know. The observable universe is like a vast, cosmic ocean, and our current knowledge is just a small island within it. There's so much more to explore and understand. Expansion of space, why the edge moves. The universe is expanding, and this expansion is causing the edge of the observable universe to move away from us. This isn't like objects moving through space, but rather space itself stretching. Think of it like dots on an inflating balloon. The dots move away from each other as the balloon expands, but they aren't moving across the balloon's surface. Similarly, galaxies move away from each other as space expands. The rate at which the edge moves is determined by the rate of the universe's expansion. This rate isn't constant, it's accelerating. This acceleration is caused by a mysterious force or energy known as dark energy. Dark energy makes up about 68% of the universe's total energy and matter content. Its exact nature is still unknown, but it's driving the expansion of the universe and, consequently, the movement of the edge of the observable universe. The edge of the observable universe is the farthest point from which light has had time to reach us since the beginning of the universe. As space expands, the distance between us and the edge increases. This means that light from objects at the edge takes longer to reach us. In fact, the edge is moving away from us faster than the speed of light. This doesn't violate the theory of relativity because it's space itself that's stretching, not objects moving through space. The implications of this are profound. As the edge moves away, the observable universe grows larger. However, the light from objects at the edge becomes redshifted, meaning it stretches into longer wavelengths as the universe expands. Eventually, this light becomes invisible to us. This means that, in the far future, the observable universe will appear empty, with only the Milky Way and its immediate neighbors visible. The rest will have moved away so fast that their light can't reach us. Cosmic horizon, where information cannot reach us. The observable universe is a vast expanse, but it's not infinite. There's a boundary, a cosmic horizon, beyond which information cannot reach us. This isn't a physical barrier, but a limit imposed by the speed of light and the age of the universe. Think of it like a foggy night. You can only see as far as your headlights allow. In the cosmic sense, our headlights are the light that has had time to reach us since the beginning of the universe. The cosmic horizon is not a fixed boundary. It's more like a moving target. As the universe expands, the distance from which light can reach us increases. However, the light from objects beyond this horizon is still traveling towards us, but it hasn't had enough time to get here yet. It's like waiting for a letter from a friend who lives far away. The letter is on its way, but it hasn't arrived yet. The concept of the cosmic horizon is crucial for understanding our universe. It's not just about what we can see, but also about what we can know. Information, in the form of light or other signals, is the only way we can learn about the universe. Beyond the cosmic horizon, we are effectively in the dark. It's like trying to solve a puzzle without all the pieces. We can make educated guesses, but we'll never be certain. This doesn't mean that the universe beyond the cosmic horizon is unknowable. It's just that we can't gather information about it yet. As time goes on, more of the universe will become visible to us. It's like waiting for the fog to clear. Eventually, we might be able to see more, but for now, we are limited by the cosmic horizon. It's a reminder that our understanding of the universe is always evolving, always expanding, just like the universe itself. What lies beyond? Theoretical infinite structures. The observable universe is a vast expanse, but what lies beyond its edges is a topic that sparks immense curiosity. Theoretical infinite structures offer some intriguing possibilities. One concept is the idea of a multiverse, where our universe is just one in a vast number of universes. Each universe could have its own set of fields and interactions, and perhaps even different physical constants. This idea isn't just science fiction, it's a serious consideration in modern cosmology. For instance, eternal inflation theory suggests that universes bubble up and expand within a larger, inflating multiverse. It's like a cosmic foam, with each bubble being a universe. Another fascinating idea is that of an infinite universe. If the universe is infinite in extent, then everything that can happen does happen, somewhere, at some time. This leads to mind-boggling implications. For example, there could be exact copies of you, me, and everyone else, living out their lives in some other part of the infinite universe. This isn't just a wild guess. It's a direct consequence of certain interpretations of quantum mechanics and cosmology. It's like an infinite cosmic copy machine, making duplicates of everything. Infinite structures also appear in mathematical models of the universe. For instance, some theories suggest that the universe might be finite but unbounded, like the surface of a sphere. In such a universe, if you travel far enough in one direction, you might end up back where you started. This is similar to how, if you travel far enough along the surface of the Earth, you'll circle back to your starting point. It's a bit like a cosmic version of a video game where the world wraps around on itself. These ideas might seem abstract, but they have real implications. They challenge our understanding of reality and push the boundaries of what we consider possible. They also drive scientific research, as scientists seek to test these ideas and uncover the true nature of the universe. It's an exciting time to be exploring these questions, as new technologies and theories offer fresh insights into the cosmos. The edge of the observable universe is just the beginning. Multiverse possibility bubbles beyond our horizon. The idea of a multiverse, or multiple universes, has been a topic of fascination and debate among scientists and philosophers for decades. One intriguing aspect of this concept is the possibility of bubbles beyond our observable horizon. These bubbles, or pocket universes, could be entirely separate from our own, each with its own set of physical laws and constants. The notion is rooted in the idea that the Big Bang might not have been a singular event but rather one of many, each giving rise to a distinct universe. Inflationary theory, a framework that describes the rapid expansion of the universe immediately after the Big Bang, provides a plausible mechanism for the formation of these bubbles. According to this theory, the universe underwent a period of exponential growth, driven by a scalar field called the inflaton. This rapid expansion could have caused quantum fluctuations to be stretched out, leading to the formation of separate, causally disconnected regions. These regions, or bubbles, could have evolved independently, each with its own unique properties. The concept of these bubbles is not just theoretical speculation. It is supported by mathematical models and simulations that explore the implications of eternal inflation. In this scenario, the universe is seen as a vast, ever-expanding multiverse, with our observable universe being just one of many bubbles. Each bubble could have different initial conditions, leading to variations in the fundamental constants of nature, such as the strength of gravity or the masses of elementary particles. This diversity could explain why our universe appears finely tuned for the existence of life, as other bubbles might not have the right conditions for complex structures to form. One of the most intriguing aspects of this idea is that these bubbles might be detectable, at least in principle. If two bubbles were to collide, the interaction could leave observable imprints in the cosmic microwave background, CMB, the afterglow of the Big Bang. Scientists have been searching for such signatures, and while no definitive evidence has been found yet, the search continues. The discovery of bubble collisions would provide strong evidence for the existence of a multiverse and revolutionize our understanding of the cosmos. Until then, the idea remains a fascinating possibility, one that challenges our notions of reality and our place in the universe. Why we cannot observe past the limit. The observable universe is a vast expanse, but it has a boundary. This boundary isn't a physical wall or barrier. Instead, it's a limit set by the speed of light and the age of the universe. Think of it like a cosmic horizon. Just as the horizon on Earth limits how far you can see, the observable universe's boundary limits what we can observe. Light takes time to travel. The further away something is, the longer it takes for its light to reach us. The observable universe's boundary is defined by the farthest light that has had time to reach us since the beginning of the universe. This is why we can't observe beyond this limit. It's not that there's nothing out there. It's that the light from those regions hasn't had enough time to reach us yet. The universe is about 13.8 billion years old. In that time, light could have traveled about 13.8 billion light years. However, the observable universe is larger than this. Due to the expansion of the universe, the boundary of the observable universe is now about 46 billion light years away. This means that the light we see from the boundary has been traveling towards us for 13.8 billion years, but the distance it has traveled is much greater. Another reason we can't observe beyond this limit is cosmic inflation. In the early universe, there was a period of rapid expansion. This expansion stretched space itself, making some regions move away from us faster than the speed of light. As a result, the light from these regions can never reach us. This is why the observable universe has a boundary. It's not a physical limit, but a practical one. It's the farthest we can see, given the age and expansion of the universe. Tools scientists use to estimate beyond. Scientists have developed a range of tools to peer beyond the edge of the observable universe. These tools are not physical devices that can be pointed in a direction, but rather sophisticated methods and models that help us understand what might lie beyond our cosmic horizon. One of the primary tools is the cosmic microwave background, CMB, radiation. This is the afterglow of the Big Bang, a faint echo that permeates the entire universe. By studying the patterns and fluctuations in the CMB, scientists can infer the shape, size, and contents of the universe, even beyond what we can directly observe. Think of it like trying to understand the layout of a vast, foggy landscape by analyzing the patterns of light that manage to penetrate the fog. Another crucial tool is the concept of inflation. Inflation is the idea that the universe underwent a period of exponential expansion in its earliest moments. This theory helps explain why the universe looks the way it does and provides a framework for understanding what might lie beyond our observable bubble. By studying the implications of inflation, scientists can make educated guesses about the structure of the universe on scales far larger than what we can see. For instance, inflation suggests that our universe might be just one in a vast multiverse, with each universe having its own set of physical laws. While this is still speculative, it's a powerful tool for pushing the boundaries of our understanding. Mathematical models also play a significant role. Scientists use complex equations to simulate the behavior of the universe under different conditions. These models can predict what might happen at the edges of the observable universe and beyond. For example, they can explore the implications of different types of dark energy or the behavior of black holes on cosmic scales. One famous model is the lambda CDM model, which describes the evolution of the universe in terms of dark energy, lambda, and cold dark matter, CDM. By tweaking the parameters of these models, scientists can test various scenarios and see which ones align with our observations. Lastly, scientists use the concept of cosmic topology to understand the shape of the universe. Topology is the study of the properties of space that are preserved under continuous transformations. By analyzing the large-scale structure of the universe, scientists can determine whether it is flat, open, or closed. This information can provide clues about what lies beyond the observable universe. For instance, If the universe is finite but unbounded, like the surface of a sphere, it might mean that if you travel far enough in one direction, you could end up back where you started. This is a mind-bending idea, but it's a real possibility that scientists are actively exploring. What next-gen telescopes may uncover? The next generation of telescopes, currently in development or planned for launch, promises to push the boundaries of our cosmic understanding. These advanced instruments are designed to peer deeper into the universe than ever before, potentially uncovering secrets that have remained hidden. One such telescope is the James Webb Space Telescope, JWST, which, despite being already launched, represents a significant leap forward in technology. It is equipped with infrared capabilities that allow it to observe some of the most distant events and objects in the universe, such as the formation of the first galaxies. By studying these ancient structures, astronomers hope to gain insights into the early universe and its evolution. Another promising project is the Nancy Grace Roman Space Telescope, set to launch in the near future. This telescope will have a field of view that is 100 times greater than the Hubble Space Telescope, enabling it to survey large areas of the sky quickly. This wide-angle view could lead to the discovery of previously unknown celestial objects and phenomena. Additionally, the Roman Space Telescope will study dark energy and dark matter, two of the most mysterious components of the universe. Understanding these elusive substances could revolutionize our understanding of cosmology. On the ground, the Extremely Large Telescope, ELT, and the Giant Magellan Telescope, GMT, are under construction. These telescopes will have primary mirrors measuring 39 meters and 25 meters in diameter, respectively. Their immense size will allow them to collect more light and achieve higher resolutions than any existing optical telescopes. With these capabilities, they will be able to study the atmospheres of exoplanets, search for signs of life, and observe the earliest stars and galaxies. The data collected by these telescopes could provide answers to some of the most fundamental questions in astronomy. Moreover, advancements in technology are enabling the development of new types of telescopes. For instance, the Laser Interferometer Space Antenna, LISA, is a proposed mission to detect and observe gravitational waves in space. Gravitational waves are ripples in spacetime caused by massive, accelerating objects, such as black holes or neutron stars. By studying these waves, scientists hope to learn more about the nature of gravity and the dynamics of massive celestial objects. The insights gained from LISA could open up entirely new avenues of research in astrophysics. As we wrap up our journey to the edge of the observable universe, let's recap what we've explored. We've seen how the universe is expanding, carrying galaxies away from us at incredible speeds. We've pondered the concept of the cosmic microwave background, the afterglow of the Big Bang that gives us a snapshot of the early universe. And we've wondered about what lies beyond our cosmic horizon, where the unknown awaits. It's mind-boggling to think about, isn't it? The universe is so vast and mysterious, and yet, we are on a mission to understand it better. If you've enjoyed this journey with me, first I'd love to hear your thoughts. Drop a comment below and let's discuss what fascinates you the most about the cosmos. And if you're hungry for more, stay tuned. In our next video, we'll be diving into the mysteries of dark matter and dark energy, the invisible forces that make up most of our universe. It's going to be another mind-bending adventure, so make sure you're subscribed and ready to explore. Until then, keep looking up. The universe is waiting, and who knows what we'll discover next. See you in the next video.